Hello again. I said that I would go through some practice problems on circular motion just to show you what the formulae look like in regular use, so let's make that happen. And they start us with a couple like factual knowledge problems, which is all right. Let's see what we can do with these. So they say an object moving in a circular path, fine, we've been talking about that already. And three statements, and we're supposed to say which ones are true. The direction of the velocity is tangential to the circumference of the circle, meaning it's a tangent to the circle. That means the velocities look like that, and like that, and like that. This is true. Anytime you're going around a circle, the direction that you're going at any point on the circle is in line. Oop, I have to not use that. It gives annoying colors. Your direction of motion is always in line with the circle and at a tangent to it. If you think about something like mud on a bike wheel, this is the direction that the mud would fly off if the wheel was spinning, and that's because each of those particles of mud has a tangential velocity, and if it loses its grip on the wheel, it just continues to move in a straight line because Newton's first law says objects that are moving continue moving in a straight line unless something acts on them. So anything that flies off a circle goes in a straight line like that. That's what we call tangential velocity. So number one, yep, true. Number two, they say the direction of acceleration is opposite the direction of the velocity. So that would mean if you're going this way on a circle, then your acceleration is directly opposite that. Well, if that were true, every point on a circle would continue to travel in a straight line, which would mean no circular motion. Also, it would mean that you'd slow down and stop if the acceleration kept going like that, so no. The real acceleration when you're moving in a circle is in towards the center. So it'll be like that. When you get to this point, it's in like that. Think about what gravity does if a moon's orbiting a planet or a satellite's orbiting a planet. It's always straight in towards the middle. So what we really say for the acceleration is that it's radially inward. Radial means it's shaped like a radius, so it goes from the center to the edge, and inward means it points in, not out. So number two, no. And number three, the direction of the net force is radially outward. No, the force is also straight in. Your force and your acceleration should always be in the same direction. Your net force and your acceleration should always be in the same direction. That also is radially inward. So 3 is wrong, only 1 is true. There we go. One more about this. Now they're talking about traveling in a circle at constant speed on a horizontal surface. So this is like we have a tabletop, and on the table something is going around in a circle. It could be a car on a little track, or there could be a magnet in the middle or a string, but we have something rigged so that it runs in a circle horizontally. And they ask direction of the net force. Well, we just saw that. The net force is always in towards the center, so it'll be that way and that way, like gravity. Always in towards the center, or we call it radially inward. Fair enough? All right. Now we get to a few that are an actual number crunch, so let's see what we can do with these. A winch on a crane has a diameter of 24 centimeters. First, I'm going to turn that into meters. It's 0.24 meters. Next, because all of our formulae use radius instead of diameter, I'm immediately going to cut that in half and say 0.12 meters. I promise you we're going to need the radius long before we need the diameter. And they say winch is being used to lift a bucket at a speed of 0.96. So what's happening is we have a winch roller up here, and there's a cable hanging from it, and we're lifting some stuff down here. They're saying if this winch is sucking up cable at a rate of 0.96 meters per second, That's our tangential velocity. This cable's going up at 0.96, that cable's going up at 0.96, and here where it starts to wrap around the roller, that's 0.96, and all the way around the circle, the velocity has to be 0.96. So that's our V, or you can write VC if you want to. 0.96 meters per second. And they're asking us for the period of rotation, which is what our formulae call capital T. So, do we have a formula that combines VC and T? Yes, we do. VC is 2 pi r divided by the period. We know everything in this except the period, so we can solve for the period. Now, if you want to isolate T before you go any further, which is a reasonable thing to do, you would probably multiply by T on both sides to get it out of the denominator. That would get you TVC equals 2 pi r, and then you would divide both sides by VC. And you get that the period is 2 pi r, like how big the circle is you're trying to go around, divided by how fast are you going around it. And if we solve that, we get 2 pi, our radius is 0.12, our velocity is 0.96, and out come the calculators. 2 times pi times 0.12 divided by 0.96, 0.785398, and it's a period, so it's an amount of time. It's measured in seconds. And finally, this had 3 sig digs, this had 3 sig digs, so I know I rounded the radius here to, I only gave it as 2 significant digits, but really it should have 3, that's my bad. So our finished answer should have 3 significant digits, and it should be 0.785. Okay, here, carriages of a Ferris wheel travel at 1.86 meters per second. So again, a Ferris wheel is a big circle, and they say that the cars on it are going around at 1.86 meters per second. That's a velocity. And the wheel radius is 6.25 meters. And again, they ask for the period. Well, same formula as before will help us here. Velocity is 2 pi r divided by the period, multiplied by t, divided by velocity. And we pretty much got it. 2 pi times, they said our radius is 6.25. Velocity is 186. 2 times pi times 6.25 divided by 1.86. And I get the period is 21.1. 3 sig digs, yeah. So with 3 significant digits, it's 21.1 seconds. There we are. Okay, cyclotrons are what you're going to see in this unit pretty soon. This is a device where you take a charged particle, like an ion, or an electron or something like that, throw it into a magnetic field, and you can get it to run around in a circle. And they follow the same formula as anything else we do, except they're blindingly fast, and the accelerations on them are usually quite high. So this object has a velocity, whatever this ion is, of 2.8 times 10 to the 6, 2.8 million meters per second. Sorry, I said 6, I wrote 8. Let's fix that. And its acceleration is an equally ridiculous 1.5 times 10 to the 12 meters per second squared. They want radius, and we know we have an acceleration formula that says your acceleration is always v squared over r. We know the acceleration, we know the velocity, we should be able to solve this for r. And just like in the previous example, if we multiply both sides by r, that gets us RAC equals v squared. And then, if we want r alone, divide both sides by the acceleration. So, the radius of our circular path would be v squared over the acceleration. V is 2.8 times 10 to the 6. Don't forget to square it. And our acceleration is 1.5 times 10 to the 12. So 2.8 exp6 squared divided by 1.5 exp12. I get the radius of 5. Everything has 3 sig dig, so 5.23 would be my rounded number. 5.23, and it's a radius, so it's measured in meters. It's the length of our path. Or the radius of our path, sorry. Okay. I kind of think this question is broken, number 6. I'm going to skip it. I tried it out earlier, and I ran into a problem where either there isn't enough information or they're wanting you to assume something that I wasn't very comfortable assuming. So if you're freeze framing this and wanting to work through these problems yourself, I kind of recommend you skip number 6. It's a little sketchy. But this number 7 is breathtakingly hard, and I thought you might enjoy doing that one. Or whether you enjoy it or not, you might get something out of it. So let's see if we can handle this. And it's a simple question with only one number in it. What altitude does a satellite orbit the Earth if its orbital period is 2.5 hours? Now, I want to have a lot of space, so I'm going to jump to the whiteboard with this one so we have more room. Okay, so we're talking about a spacecraft, a satellite or something, with an orbital period, that's t, of 2.5 hours. And the question is, how high is it? For now, there's a little more to this that I will get to in a minute, but for now, let's pretend they're just asking for the radius. As in, how big is the circle around the Earth? So this blue ball is the Earth. That is exactly what Earth looks like. And our satellite's going around the Earth, and we want to know what is the radius of that big circle it's following. That's our R. And they've given us the period. Unfortunately, they've given it to us in irritating units. We don't normally want to work in hours, we want to work in seconds. Most of our formulae work with meters and kilograms and seconds as our units. So if you have 2.5 hours, you can multiply that by 60 to find minutes. So the period they're talking about is 150 minutes. And if you multiply by 60 again, because there's 60 seconds in a minute, you get that our orbital period is 9,000 seconds. So that's how high up our object is. Sorry, that's not how high. That's how long it takes to go around an orbit once. And what can we find from that? We have period. We're trying to find our radius. We don't know our velocity. That's a bit of a problem. But here's something we do know. We know that if you're orbiting like this, the only force that can keep you going in an orbit like this is gravity. So the force that's pulling you in is a gravitational force. Anything that's orbiting the Earth is not burning its engines constantly to stay in orbit. You'd run out your propellant in a matter of minutes if you tried to do that. So there has to be just Earth's gravity is pulling you in, and that is your centripetal force. That's how we're going to get started. Gravity is the force that's pulling you into the circle. Now, there's a formula for gravitational force that you may have had some experience with. It says that gravitational force is the gravitational constant times the mass of whatever you're orbiting, or whatever planet you're around. In this case, I'm using E for Earth, times your own mass. I'm putting ms for mass of the satellite, divided by radius squared, like the distance between you and the object. And that equals, you remember a formula for centripetal force? For this, you can put the acceleration is 4 pi squared r over t squared. And if you want to make that a force instead, you put an m in front of it. So all of this, 4 pi squared r over t squared, is what we call AC. And anytime you want to find a force, you can write an acceleration and then just throw in an m in front. Now that mass is for the object that's accelerating, which means it's for the satellite, not the Earth. So, that's horrendous. Can we solve this and get r? We have r in 2 different places, which is a little upsetting, and there's enough other variables in here to choke a brontosaur, but let's see if we can clean this up a little bit. One thing I notice is we have the mass of the satellite on both sides of this equation. We can lose that. We can divide both sides by ms. It turns out it doesn't matter how big your satellite is when it comes to orbiting it. Once you get it up into space, they'll all orbit at the same rate. So mass doesn't matter. If we're trying to get r, all our r's together, we could probably get r out of the denominator. What if we multiplied both sides by r squared? Those r squareds cancel. And what do we get now if we clean this up? On the left, we have the gravitational constant times the mass of the Earth. On the right side, we have 4 pi squared. We have r times r squared, which makes r cubed, over the period squared. So that's good. At least we have all our r's in one place now. If we want to solve this for r, we have to get rid of the 4 pi squared and the t squared, which is not that difficult, actually. We can multiply this side by t squared over 4 pi squared. We're doing that because then our t squareds will cancel and our 4 pi squareds will cancel. And of course, if we do that, we must do the exact same thing on the other side. So t squareds gone, 4 pi squareds gone. If we do all that, we're left with r cubed equals t squared g m e over 4 pi squared. Wow. Okay. Do we have all these numbers? I'm going to need another line for this. There's a lot to write here. Come on. To get that square in there, or I'll have to write it again. We don't want that. Okay, so the period is 9,000 seconds. Don't forget to square it. G is the gravitational constant. It's 6.67 times 10 to the minus 11. That's true all over the universe. It's just it's not attached to any particular planet. It's just how strong is gravity in our universe. The mass of the Earth is 5.9, is it 7 or 8? On our sheet it's 5.97. I learned 5.98 at some point, but I guess we lost weight. 5.97 times 10 to the 24 kilograms is the mass of the Earth. Down here we have 4 pi squared. We know what pi is. I'm not going to write that out. So all that goes into the calculator, which should only take me about 9 minutes to do. 9,000 squared times 6.67 exp 11 minus times 5.97 exp 24. I I didn't forget to square anything, did I? Nope, looks like we're okay. Divided by 4 and divided by pi squared. So what that gets me is r cubed is 8.17 times 10 to the 20. But we don't want r cubed, we want plain old r. If you want to uncube something, you have to cube root it. So if we cube root both sides of this, we'll get just r. And the number then is 9,348,497 meters. Now, that isn't our finished answer, but it's darn close. Let's talk about what that means. Need to clear some space, so we'll get some of this manipulation out of here. Hit back up a little bit if you want to see that again. Okay, so let's fix this a little bit. All right, so here's Earth. And when we measure a radius for an orbit or for any circular path, it's from the center of the circle, meaning the center of the Earth, up to wherever our object is. We'll do a kind of classic satellite with the panels. There. So what this number is telling us is that it is 9,348,497 meters from the center of the Earth up to where the satellite is. But the original question asked for the altitude, and altitude is not from center to center, it's how far you are above the ground. It's just this. This is the dirt. This is where we're standing, give or take. And we just want that distance. We don't need the distance, or we don't want to count the distance from the center of the Earth up to here, and so we have to take that part off. And to do this, we need to know that the radius of the Earth from dead center up to the dirt, it's on your data sheet, the radius of the Earth is 6.37 times 10 to the 6 meters. In other words, the radius of the Earth is about 6,400 kilometers, and up to this satellite is like 9,300 kilometers, so once we subtract this amount off, the remaining amount will be our height, or our altitude. So, 9,348,497 is the total distance. From that, subtract 6.37 times 10 to the 6. Fortunately, calculators don't mind if you give them some numbers in regular notation and some in scientific. If we subtract 6.37 times 10 to the 6 from that, we get that the pink distance, the height above the ground, is 2,978,497 meters. You could put that in scientific notation if you wanted and say 2.97. Trying to remember how many significant digits this question originally had. 1 second. They gave us 2.50 for our period, so our answer should have 3 sig digs, meaning I should round this to 2.98. There's our 3 significant digits. 2.98 times 10 to the 1, 2, 3, 4, 5, 6 meters would be one way to give the altitude. Or, because a million meters is a megameter, you could say this is 2.98 megameters. Or, if you don't want to weird people out by using megameters, because hardly anyone ever talks about those, you could take this number divided by 1,000 and get 2,980 kilometers. I'd say the scientific notation and the kilometers are pretty reasonable, and The megameters are fine if you're talking to other physicists, but most people don't think about megameters very much and they won't appreciate this. So, this was a super involved problem that pulled out a lot of stuff that we haven't talked about much otherwise, like gravitational force and complicated equation solve. But at the center, it was still about using centripetal force, and if this didn't bother you, nothing else in this section is going to. As always, if you have any concerns about this, get a hold of the instructor. If there's any other videos about this stuff that you wish we had made and haven't made, tell us about that. We'd love to hear it. We'll see if we can make those happen. So, have fun with the new unit.